Hello, welcome everyone. My name is David Boxfoldy. I'm a technical director at Cognizant Softvision. And as part of the Programmers Week, I'm going to talk a little about real-time video and how that works on the internet. So this is a very high-level conversation. So the area of real-time video and real-time media streaming is very broad. It covers a lot of ground on a lot of different topics. So this is not meant to give you an expert's view on it, but rather give you an overview of all the pieces involved, what they're doing, and why we're structured it this way. It's structured into three parts. So one, I'll talk briefly about the how encoders and encoding works, specifically around video, because it's important to know this. What protocols are involved, and finally, how some network topologies around real-time video and real-time media, how it actually looks like, and kind of some of the challenges you have and how they've been tackled. At the end, there will be a question period. So the talk is about 40 minutes or so, give or take. So we should be able to kind of go through this a fairly brisk pace. So let's start with the media encoding. So the concept of media encoding is basically taking a set of, how should we say, disparate data types, in this case video and audio, and encoding it and often compressing it into a format that's suitable for distribution across either the internet or some other media. So it comes from stems from signal processing field, where you take a signal and you basically encode it using some encodec, as it's called, into a new format. When it comes to media, specifically video and audio, it's useful to think about audio and video as separate. So generally, the best way to think about it is that think of video as a set of discrete 2D units. So that's a picture, basically, that is supposed to be presented or captured at a certain frequency, versus audio, which is can be perceived as a continuous stream. So for example, let's give an example to kind of explain this a little bit further. So say that you captured a video at a certain frame rate. So you have, say, 30 pictures, but you're only able to display 5 of those. Most people will be able to infer what the content in between those frames would be, and still be able to kind of piece together an understanding of what you're looking at. Now, audio, on the other hand, if you captured audio at a certain sampling frequency, and then you only distribute, say, maybe a third of those samples, it would be very disruptive to the listener of that audio to hear what actually was going on. And because of that, the encoding restrictions and the way you approach it is different. The other challenge, as of course, is this video is orders of magnitude larger than audio. So it requires you to use different techniques, more aggressive compression, as well as the impacts the needs of the network, both in terms of bandwidth, but also in latency. So what are these codecs then, these encoders and decoders that I'm talking about? Well, it's basically a set of common standards for packing up these signals into a digital format and then unpacking them. So you might have heard some common terms like H.264 or MPEG-4 or H.265, or maybe MP3, if you remember that, or AAC. These are all codecs. So they all have a task of taking a raw media, so that's an uncompressed video frame or an uncompressed piece of audio, compressing it and encoding it in some format. And then on the receiving side, you would follow the same kind of mechanisms, the same algorithms to unpack and uncompress this. Of course, these are all lossy formats that's listed here. There are codecs that are lossless as well, but for real-time video, lossy is the only really thing you're interested in, because you're interested in very high compression rates. So there will be some loss, but it relies on the fact that human beings are pretty bad at precision, and you're more interested in certain aspects of the raw data than others, and it leverages that. And for this specific area, video compression and how video compression works is the really important piece, because it does have an impact on both the protocol stack as well as the network topologies that we'll be discussing later. So I'm going to go into that again, high level, and talk a little bit about how video compression works in modern video codecs. So this is a common video, a common video stream. So here, in this case, you have a very simple video stream consisting out of a person with like a ball coming in. So there's some movement there. There's some static object, the person. Video encoding usually works, and specifically in these H.264 and H.265 codecs, it works by capturing the differences, encoding the deltas within these things. There's also encoding within the frame as well. I won't talk too much about that because it doesn't really impact us on, in this case, because video encoding from real-time streaming perspective, it's just it doesn't matter. But similar to how you do image compression, you would also do video compressed within the frame. But the differences, on the other hand, are quite important. And it's important to kind of understand how that works and why we do it this way. So the way that these codecs work is that they will generate something called a keyframe or an anchor frame, which contains the whole picture. As you can see here on the first frame, that it encodes the entire picture, including the difference, into one frame. And then there is a concept called prediction or predictive frames, where basically the difference, only the difference, is encoded. So basically layer this thing on top of the anchor frame, layer this thing on top of the anchor frame, layer this thing on top of the anchor frame. You can see how they all refer back to the keyframe. And that way you can, by sending only the differences, you are able to reduce the amount of data you need to send for any one frame. These can also refer back into the hierarchy as well. So you could have a forward frame in the future refer back to a change in a previous frame. And that way, say that you have, in this case, with this ball object is getting revealed, that could be contained in the future frame and then referred to back into these frames and just moved or repositioned within the stream, so to speak. This entire set is sometimes referred to as a group of pictures or a GOP, which means that it's an indivisible unit. You need to have access to all of these to kind of decode all of these frames. The predicted or frames that only contains the difference is sometimes referred to as a P frame. There's also another type of frame called a B frame, which can refer to multiple, both forward and back, which is common in both in H.264 and H.265. It's not important to know this for video streaming, but it's just for a piece of information to kind of, if you bump into that term. So for example, what does this encoded and output? Well, here's an example of an H.264 video stream, and for video streaming on the internet in real-time video, as we do right now, or any kind of other video conferencing or chat solution you've been using, most likely 99% of the time is going to be using H.264 MPEG-4 codec to do this. So that's why I use this as a reference going forward. So this is what a H.264 encoder stream looks like at a high level. It's basically outputting a set of chunks called NALUs. That's referred to a network abstraction unit, which is basically a small piece of information. So here, for example, you have an IDR frame leading up, which is like a TLV, like a type length value configuration. And that's basically a keyframe. That's the H.264 lingo for a keyframe. There's some informational content. There's a predicted predicted frame, SI, which is another informational content, kind of tells the decoder how to handle these predicted frames, etc. Which makes it a chunked set of data. All of these can be individually decoded and provided to the decoder because they encapsulate all the information needed to do this, right? So initially, this wasn't done for networks at all. This was done for Blu-ray discs, where you need to read a certain amount of information off a Blu-ray disc, and these kind of packets were handy for this. But then they realized that this is also great for sending video over the internet. So all decoders or codecs you bump into today will use this bitstream format as well. It's just that will be structured slightly differently. So how does this then map into like real-time media, right? So it's great for Blu-rays, great for like streaming, like playlists, like YouTube or whatever on the internet. But for real-time, there's a little bit different requirements here. So all of this is based around a very simple scenario here that kind of gets more complicated as we go. But it's basically two participants in a peer-to-peer connection. So it's Eve, who is chatting with Lucy. Lucy's a bit shy, so she's not sharing out her video, only her audio stream. So the video direction is one way only, from Eve to Lucy. They have two computers that they use, public IP addresses communicating. So as you can see here, there's every single, most of the real-time video communication that's happening, or media communication happening, is using an IP network. And for the IP network has this, like the internet network we use and the protocol we use on the internet, has a couple of interesting characteristics. One of them is that it's not a reliable mode of transport, right? So if you send an IP packet from, say, Lucy sends one to Eve, there's no guarantees that this will actually end up there. She just knows that send this piece of data to Eve, who is at this IP address, right? But she won't get any report or anything like that if it drops or anything like that. And she also won't know how long it took to deliver this IP packet. So she sent something over, maybe it took 50 milliseconds to get it there. Maybe it took 5 seconds. And thirdly, she doesn't know which order these will be received by Eve. She might send 4 packets with really important data, and so she sends finally a last packet, a 5th packet, and that will be received before the other 4 packets. So these are, of course, makes it really difficult to use IP packets straight up, right, for any kind of communication or data exchange. So that's why usually IP communication is done using one of these two protocols, TCP and UDP, or UDP, I should say. And they both have different characteristics that may or may not make them suitable for real-time communication. So TCP gives the illusion of a reliable transport. So it gives you a reliable delivery that maintains the ordering of the packets that you send. So if you send packet 1, packet 2, packet 3, you're guaranteed to be on the receiving side will receive them in the order that you sent them. It also guarantees the delivery of these, right? So that they make sure that if you send a packet, the client, the receiver, will act them and say, "Yep, I got your packet. Continue." So that's great. Unfortunately, it also has a couple of consequences. And one of them is that it has an unpredictable latency because it needs to preserve ordering, and the retransmission behavior and the retries and the packet loss detection is bounded both on my side as the sender, but also on the receiver side. So it makes it very difficult to predict what the latency is going to be for these things. And the other one is the data rate. So the data rate is also not predictable. I can't reliably determine what my data rate would be in the future using this connection, because there might be network conditions that will impact this, right? So maybe for real-time video, where you don't necessarily care if all the packets that you send are received, we'll get to that later, it might not be the best choice. The other one is UDP, and UDP is a very thin layer on top of IP. It's just some extra information, basically doing nothing for you. It basically maps between, it adds the concept of a port or a receiving port on the receiver side. It doesn't have a reliable delivery mechanism, so it won't tell you if it drop packets. Up to you to figure it out. Packets can be delivered in any order, but it does have the advantage of you being able to have full visibility into the latency and the data rate of the things that you sent, because this can be provided back to you, right? You will, if you have a protocol on top of this. And this is where we get to the first of many protocols that real-time video leverages, right? And that is RTP, the real-time streaming real-time protocol. So this is roughly what the protocol stack looks like. So you have the bitstream nulls. So these are the videos in this case, so it could be audio as well. Package it up into RTP packets that then get sent over UDP, which then gets sent over IP. It's very, very lightweight. It contains not too much information besides the RTP header, UDP headers, and encoded media. And it gives you a logical model on top of this, which is streams-based. So RTP defines a set of streams. So that, think of them as individual logical media streams. So that could be like video stream, audio stream, etc., etc. Each one of these streams have a sequence. So that's the order of packets. So this is packet 1, this is packet 2, this is packet 3, this is packet 4. And also has a timestamp when this packet was generated. So that would basically be in relation to the stream. So for example, if you started streaming, say, a video, you would have a timestamp for every single, say, frame. So you would have one, if you have 30 frames per second, you would have 33 milliseconds, 66 milliseconds, and so on in this thing. And an RTP packet can contain multiple streams, not just one. So it's a very simple protocol, but it allows you to detect packet drops within this sequence, because you can see if you get them out of order, right? Or don't receive them at all. And you can also see roughly what is the media latency. So this is the timeline of playback here. But as you might have seen, there is no provision within RTP to tell the receiving party where and how and when the data was received. So that's not contained. It's just a set of sequence of packets with a timestamp or timeline associated with it, and they can contain multiple streams. It's a very simple protocol. So obviously, it won't do everything we needed to do. We kind of need to extend it a little bit. So that's where RTCP comes in. So RTCP is a control protocol associated with RTP. So it provides this information. Specifically, it provides statistics around streaming. So in the case, for example, where one packet gets lost, RTCP allows the receiver to respond back and say, hey, great job sending me these packets. I got 2 or 3 out of the packets since I last sent you one of these reports. This is, as it also will contain the wall clock time of the sender, so that you can kind of measure latency. So you can see here is the time when I made this RTP packet, so you can see how long it took to deliver these things, as well as these delivery statistics. So these packets are called receiver reports or sender reports. But it's, as you can see, it gives us some more information. We can measure latency, and we could measure throughput, like how many packets we sent versus how many we received. But it does have some limitations if you actually start looking at how this maps back to a video stream. So this is a normal kind of video stream setup. You have Eve here. She's starting to send her video out. you can see she sends one keyframe down, gets split up to two RTP packets, that gets bundled into two UDP packets. It gets received on the other side and reconstituted. There's some predicted frames following, etc., etc. All hunky-dory. But what if we get a packet loss in the scenario we just saw here? What happens then? So, so we see here it's that she received the first anchor frame. She gets a couple of predicted frames, but she drops the second anchor frame. Now, intuitively, you'd think that, okay, there's one packet loss, not a big deal, right? But what actually happens is that if it's the anchor frame, all the frames that we receive after that, all the packets containing frames we receive after that, we can also not decode, right? Because we don't have the initial frame, as you saw in the H.264 layout. We only have the differences. The differences to what? So we have to scrub all of those, right? No worries, you know. Lucy eventually kind of shoots off a receiver report packet back to Eve, saying like, hey, you know, I lost 2 out of 3 frames, or, you know, 500 out of, you know, 2000 or whatever the frequency is. And Eve then, not knowing which these frames are, right, would look at this and say, hey, oh wow, I'm saturating the data pipeline here. I'm going to dial back my encoder so that I don't send as many bytes, right? And so many bits. The most common approach to do that is reduce the frequency of keyframe generation. That would be the prime way of doing it. I'm going to stop sending you keyframes because they are usually 10 to 50 times larger than the predicted frames. So she'll stop sending as many keyframes, which makes it worse for the receiving part. So this is RTCP, the default RTCP. So it's not going to solve our problem. We will be able to find out that we didn't get all the packets, and both parties will be able to send in to share this information, but they won't effectively be able to deal with this problem. Of course, lucky for us, RTCP and RTP provides a very robust extension mechanism, an ability to extend the protocol with new features and new flags and new payloads. And one of these is called AVFP, which is a protocol extension that allows us to do the right thing, which is what would we like to do? Well, we want to tell, as Lucy, we want to tell Eve that we need a new new keyframe, because if we lose a predicted frame, it's not a big deal. You don't have to resend that, but the keyframe we do need. So we need some way to catch up to the stream, the real-time stream that Eve is sending, right? And this is called a picture loss indication frame. There's a couple of different other variants of this, but that's probably if you're sitting at home with Wireshark or something like that, capturing frames, that's the one you'll see. You'll see a PLI. So with that, we can request a new picture frame. Please give us a new picture frame to rebuild our point in the stream, which will then allow us to quickly catch up. There's a couple of other recovery mechanisms as well involved, right? One of them is something called forward error correction, which is not super common in video, but for audio, especially the Opus protocol codec uses this. And that's exactly what it sounds. It's when you embed a small piece of data from the keyframe, or in Opus's case, it's like similar anchor mechanism, into the future frames you're sending, so that even if there's a loss, you have a certain amount of statistical probability to rebuild that frame in the future. This does increase the bandwidth needed of your outgoing RTP streams, but it's sufficiently bandwidth efficient that you would use it for audio, for example, where the data amounts are small enough to do this effectively. On the video side, there's another approach that sometimes is used, which is a feature, advanced coding feature that is optional on H.264, but mandatory on H.265 and VP9 codecs, and that's something called scalable video coding. So previously, when you encode, you would encode the whole frame at full resolution. So say that you had a 1080p frame, all the predicted frames would also be at 1080p. So, and they would all have a single frames change in them, right? Scalable video coding works by splitting the video stream into multiple, think of it as resolutions. So you would have one part containing the high resolution information, some part containing the mid resolution information, and some part containing the low resolution. But they all would be able to reconstitute the video stream. So you could layer, say, the low resolution changes on top of a high resolution anchor and get a new frame, but it would look a little bit funny, like a little bit low resolution funny. The advantages, of course, is that you could, if you wanted to, encode this low resolution anchor frame into your forward error correction packages. This is not super common, but it could be done if you felt that that was something that you thought you needed. So that's from kind of error correction and recovery approach. So let's dive in a little bit into the network. Okay, so we have the encoding piece done. Like, we kind of know how it's working. You know, the protocols are very not necessarily simple, but they're right there. We have a good understanding on how things work. Things get chopped out into packets, and there is a communication protocol called RTCP that sends the data back and forth. But how do these people, like, the example is very simple. There's two public facing IP addresses just exchanging data over UDP, which is not necessarily what it looks like, right? So this is the scenario we have been looking at so far. Lucy and Eve, they can know and see each other over the internet, and they can exchange packets freely. This is not the case for most people. Most people don't sit on a public IP address, and they're not able to exchange information like this. So before we dive into that, I want to talk a little about WebRTC. So I'm sure you guys have heard about WebRTC, and how does that, and often when people use real-time video in the browser, they'll be using WebRTC as the backing technology. So WebRTC is kind of like a grab bag of different protocols and standards and agreements. So it's a JavaScript level API that's implemented by browsers. You can use it in any modern browser. So that's basically everything except IE, I believe. And it allows you to do a couple of things. One is to kind of access the camera and audio streams of your computer or phone that you're using it on. It has the ability to create these kind of RTP streams, media streams, compressed media streams, and enumerate them. It contains a way of exchanging these between two browsers so that they can connect to each other using RTP and RTCP, compressed using audio codecs. So WebRTC defines VP8, VP9, and H.264 as acceptable video codecs, and AAC and Opus and PCMU as acceptable audio codecs. It also contains data exchange over stream control protocol, which I'm not going to talk to here because it's just used for data exchange. And it contains a piece that you might have seen called ICE, or rather I've broken out all the different acronyms here: Stun, Turn, ICE, and PCP, which is basically all the abbreviation soup that you need to kind of find and connect to peers on the internet using WebRTC. So this is an actual, what it probably looks like for most people. So they sit behind a Wi-Fi router, and they have some kind of private IP address, and they also have a public IP address, but they don't know what that is because you're behind a router that does network traversal for you and kind of rewrites your IP address for you. So how do they actually connect to each other in this scenario? Well, that's where the first acronym comes in, Stun. So Stunt Server is a server that runs publicly somewhere on the internet that allows these participants to ask the Stunt Server, hey, what's my IP address? And what port are you seeing this on? So that you'll send a UDP packet up from Lucy, for example, via the router up to the Stunt Server, and the Stunt Server looks at what the connection came from. In this case, a IP 1234 at some port, and responds back to Lucy at that port to make sure. And then there is a negotiation and kind of checking stage, right? Because the packet might not make it back to Lucy, right? But if all goes well, both Lucy and Eve can use this mechanism to find out what public IP they have and what port they have available. So this is also used as hole punching. So most routers would support this kind of behavior, right? This is when everything goes okay. There's no big things, and they can start exchanging UDP packets on this port IP combination. Sometimes when you have a firewall or some restrictive access, this won't work. All of these, the Stunt Server will just report back that, sorry, buddy, all these things are locked up. So there's a set of older and newer protocols that support this. So this is the newest one called Port Control Protocol, which is basically a protocol between your computer or device and the firewall router to open up the port that you need. So this is commonly used in the cases where there's not automatic assignment of ports and you need some kind of approval process to go through it. And that the port control protocol will be used to open up the frame. Similar as and eventually they'll be able to talk to the Stunt Server, and the Stunt Server will respond back with the IP and port that they could use. And finally, you have the worst case scenario, and that is you cannot open up a port on the firewall. It's completely restricted, but Eve and Lucy still want to exchange data over UDP. Then Turn comes in. And a Turn server is basically a relay server that runs externally on the public internet that forwards UDP packets in there on the remote server using a TCP connection. Obviously, for real-time video, this is going to have quite poor performance, and often Turn is generally not used for video, but you would use it more for audio conferences due to the performance restrictions involved. But what is actually sent over these things, right? What is the data exchange format? Well, there's two major things done, right? One is that the informational piece, like I said, Lucy assembled all her information. What does they actually send over, right? To start a session, she would know that she would need to share her ports and IP address. She would need to share her media formats and streams, because Eve might not be able to process these, right? As well as encryption keys, if there's any, if they use older SRTP, how it's structured, because when it comes to RTP and RTCP, newer versions, they sometimes send both packets on the same port versus just protocols on the same port versus using two separate ports, etc., etc. There's a lot of stuff. Well, this is done using the Service Description Protocol called SDP. It is basically a block of text with a key value text. I posted an example here of a WebRTC Service SDP blob, and as you can see, it's from that it's a lot of acronyms and secrets, and it's a fairly old protocol as well, because they were concerned of saving space by just using one letter for the keys. Jokes on them, because these things are usually like hundreds and hundreds and hundreds of lines long, so they don't really save that much space, but that's how it is. And it contains a bunch of secret kind of like hard to analyze text, like codes, like numbers and letters that don't really make any sense outside of the context. And the other piece is how is this signaling done? How is this initial exchange of these things, right? Because the SDP will encode where Lucy and Eve are located and what they're sharing, but not how they actually exchange this information. Well, or even how they hang up on each other, right? Because it's UDP. So UDP, there's no concept of closing a connection, right? Well, that signaling is actually done out of band, so there's no set standard for that, and this is what creates the kind of complexities around this, right? Is that, and why one of the main reasons why you can't say use Hangouts to talk to Messenger, for example, even though both of them are WebRTC based or RTP or TCP based platforms, because the signaling side of things are all secret. All right. So let's kind of go into like the more complex scenarios where things gets more difficult. So far, we've only been talking about peer-to-peer conversations and peer-to-peer streaming, right? But like here, for example, right, or any kind of video conference, there's no peers, right? So the naive approach might be to say, oh, okay, we're just going to have everyone connect to each other and send each other data, right? And that, of course, scales very poorly because the amount of data that needs to be sent between these it would increase with the number of participants, right? And the other challenge is, of course, is that if you remember back from 15 minutes ago when we were talking about the picture loss indication, even if you did have bandwidth to support all these combinations, you would also have to generate a lot of picture loss indication frames and generate new keyframes, etc., to have all these RTCP requests coming in be honored, right? Which would make it very taxing on the encoder as well, because you would have to run multiple encoders with multiple resolutions from multiple parties and keep track on who had what and who wanted a PLI and who wanted this and who wanted that. It really becomes unworkable, as well as measuring latency becomes challenging as well, and adapting for latency and data loss on your pipe, because the more you send, right, the more data loss you get. Usually it's not a linear relationship. There's usually great throughput and great latency up to a certain bandwidth limit, and then after that you start dropping, right? So it would be very challenging, right? So how can we fix this, right? So the simple approach is, of course, we're just going to insert a server in between, right? And that's usually called a mixer. And a mixer is basically something that takes all of the incoming streams and forwards it, collates it and forwards it to all the participants, which allows each participant to only have one connection. And it can also do things like transcoding or encoding things. Like, for example, if you had like 50 participants, for example, you might just re-encode that video into one frame and send it out to everyone, so they wouldn't have to have 50 individual video streams, for example, sent. It can layer effects on, it can do queuing, it can do a couple other things, right? Which is super practical if you're in a video conference, right? It can do recording, it can do all sorts of stuff, right? But we can actually do one better. So if you remember when it came to scalable video coding, so that we can send multiple video streams as part of our packet stream as well at different resolutions. This is what's called a SFU, or Selective Forwarding Unit, which allows us to, from one sender, send 3 separate resolutions and then have the SFU package this up to produce video streams of different resolutions, including providing packet loss indication support on the SFU side, which is how the more advanced video conferencing systems like Zoom, for example, does it, right? Which allows you to get good bandwidth usage, and as well only send the resolution that's needed and allow participants to switch between resolutions. So I guess feel free to ask any questions here at this point. So we're about time for this piece. You can do it in the QA tab there. And hopefully, while we're waiting for any potential questions, one of the things that I didn't talk about is security encryption. So encryption and security in this is done using something referred to as SRTP, but it's complicated because SRTP actually has gone through an evolution. So initially, the encryption keys would be provided out of band, but these days it's actually done using DTLS. So that's the datagram version of the TLS or SSL that you are familiar with. But that, of course, has some restrictions where if you have an SFU, for example, you might have heard the Zoom encryption issues, right? Is that the data exchange there between, if you have a mixer or an SFU in between, it'll only be encrypted between that and the mixer, and then plain text on the server, and then encrypted again between the participants. Okay, it doesn't look like we have any questions at this point. Well, thanks everyone for joining, and hopefully this was helpful to you. All right, thanks everyone.